Welcome to our channel. We are so glad you found your way here. Let us help you fall asleep. Let's begin with Europa's hidden ocean. The search for life beneath the ice. Take a slow, deep breath in and release it. Let the weight of the day fade away as we embark on an unhurried, atmospheric journey through the wonders of the cosmos. Your mind is quiet. The universe is vast, and we are ready to explore. This icy moon orbits around Jupiter, characterized by its smooth, bright surface, which conceals a dynamic environment beneath the crust. Composed primarily of water ice, extends several kilometers thick, forming a protective layer over the ocean beneath. This ocean is believed to be in contact with a rocky mantle, creating the potential for chemical interactions that may be conducive to life. Surface features exhibit intriguing patterns, including ridges and cracks, suggesting the movement of ice in response to tidal forces exerted by Jupiter's immense gravitational pull. These forces not only influence the moon's geology, but also hint at the dynamic processes occurring beneath the frozen exterior. The ocean's depth remains a subject of study, with estimates suggesting it could be as deep as 150 kilometers. Such an expanse of water may harbor conditions similar to those found in Earth's own deep-sea ecosystems, where life thrives around hydrothermal vents. The potential for life has spurred interest in missions aimed at exploring Europa. Instruments designed to penetrate the ice and analyze the ocean's chemistry might reveal whether the essential ingredients for life are present. This exploration could answer profound questions about the existence of life beyond our planet, providing insight into the evolutionary processes that shape the universe. The first recorded observations of Europa date back to the early 17th century, when Galileo Galilei turned his telescope towards Jupiter. Noticing its distinct features, he identified the four largest moons, now known as the Galilean moons. Europa, with its smooth ice-covered surface, captured his attention, hinting at a world unlike any other in the solar system. Over the subsequent centuries, observations remained limited, largely due to technological constraints. In the 20th century, advancements in telescope technology and space exploration ushered in a new era of understanding. The Voyager missions in the 1970s provided the first close-up images of Europa. These images revealed a surface marked by a complex network of ridges and fractures, suggesting the presence of a subsurface ocean. This notion was further solidified by data collected during the Galileo orbiter mission, which spanned most of the 1990s. As scientists analyzed the magnetic field data, they inferred the presence of a conductive layer beneath the icy shell, likely composed of salty water. This discovery intensified interest in Europa as a candidate for harboring life. The surface temperature, while frigid and inhospitable, masks the dynamic processes occurring beneath, where conditions may be conducive to life as we know it. The historical narrative surrounding Europa serves as a foundation for contemporary explorations aimed at uncovering its secrets. The Galileo mission marked a pivotal moment in the exploration of Europa, revealing the moon's intriguing surface and its potential for harboring life. Launched in 1989, this spacecraft embarked on a journey to study the Jovian system. Data collected indicated the presence of a subsurface ocean lying beneath a thick shell of ice. This hypothesis was bolstered by the moon's unique geophysical properties, including its relatively smooth surface and evidence of cryovolcanism. The Galileo spacecraft's instruments detected variations in the moon's magnetic field, further supporting the notion of a salty ocean potentially rich in chemical compounds essential for life. These findings ignited scientific curiosity regarding extraterrestrial habitats. The potential for a hidden ocean sparked discussions on the possibility of microbial life existing within this isolated environment. Imaging techniques revealed surface features that hinted at geological processes, raising questions about the moon's thermal activity and the interaction between the ocean and the icy crust above it. Galileo's legacy continues to inform future missions, shaping the trajectory of astrobiological inquiries and deepening our understanding of this enigmatic world. The ongoing quest for knowledge remains influenced by the foundational discoveries made during this landmark mission. The ice shell encompassing Europa exhibits a complex interplay of features, shaped by both internal and external forces. This region is marked by a variety of surface structures, including ridges and cracks, indicating the movement of the ice as it floats above the ocean below. The icy crust, estimated to be several kilometers thick, presents significant challenges to understanding the dynamics of this celestial body. Temperature fluctuations play a crucial role in shaping the surface. Variations in sunlight exposure lead to thermal stresses, which can cause the ice to fracture and reform over time. These fissures may serve as conduits for heat from the ocean below, potentially allowing for hydrothermal activity that is essential for sustaining life. Observations suggest that some regions may display a darker coloration, possibly resulting from the interaction of the ice with subsurface materials, enhancing the complexity of the surface environment. The study of this ice shell extends beyond mere observation. It encompasses the analysis of composition and physical properties. Spectroscopy has revealed the presence of various compounds, including salt, which may indicate a chemistry conducive to life. Understanding the characteristics of the ice shell will reveal the intricate tectonic processes shaping Europa's surface. These processes create a diverse array of cracks and features, each telling a story of the moon's dynamic nature. Patterns of ridges and troughs crisscross the icy landscape, indicative of tectonic forces acting beneath the surface. The movement of ice, driven by internal heat from tidal flexing, generates fractures that can extend for hundreds of kilometers. These cracks often appear in various forms, such as linear features, chaotic terrains, and circular pits. Linear cracks suggest tension within the ice, while chaotic terrains reveal a more complex interplay of forces that may involve ice being moved and reshaped. Circular pits might represent areas where warmer, subsurface material has upwelled, indicating a possible exchange with the underlying ocean. This region of Europa is not merely a frozen shell. It serves as a window into the moon's geological history and its potential habitability. Each feature holds clues about the interactions between the ocean and ice, as well as the possible influence of the moon's rocky core. Mapping these surface features aids in understanding the broader context of Europa's environment, further illuminating the potential for life beneath the thick, icy crust. Theoretical models suggest that the thickness of Europa's ice crust varies significantly across its surface, influenced by geological activity and tidal forces. These variations create regions where the ice may be thinner, allowing for interaction between the underlying ocean and the surface. The possibility of liquid water being in close proximity to the ice mantle fosters an environment conducive to chemical reactions, essential for supporting life. Simulations indicate that in some areas, the ice could be as thin as 1 to 2 kilometers, while in more stable regions, It may reach depths of up to 25 kilometers. This disparity suggests that certain locations may serve as potential access points for future missions seeking to analyze the ocean beneath. In addition to thickness, the dynamic nature of the ice shell plays a crucial role in determining the underlying ocean's characteristics. It is believed that convection currents within the ocean may drive the movement of the ice above, leading to the formation of ridges and cracks. These structures can offer insights into the ocean's composition and the materials interacting with the surface. Understanding the relationship between ice thickness and geological processes is fundamental. It not only reveals the potential for habitability, but also guides the design of exploratory missions aimed at uncovering the mysteries of this intriguing moon. Magnetic field analysis provides compelling evidence for a subsurface ocean beneath the thick ice crust of this intriguing moon. Measurements from multiple spacecraft reveal fluctuations in the magnetic field, suggesting the presence of a highly conductive layer beneath the surface. This layer likely consists of a saltwater ocean, a component critical for sustaining life as we understand it. Data collected from instruments on board missions, such as the Galileo spacecraft, indicate that the magnetic field interacts with charged particles in a manner consistent with an underlying liquid layer. This interaction implies not merely the existence of water, but also conditions that could support chemical processes essential for life. The detection of these magnetic signatures assists scientists in mapping the ocean's extent and depth, further informing the parameters for future exploration. The thickness of the ice shell, estimated to be several kilometers, poses a considerable challenge for direct observation. Yet, it also serves as an insulating barrier, potentially protecting the ocean from external impacts and radiation. These conditions create an environment where life could persist, hidden from the harshness of space. Understanding the dynamics of this magnetic field continues to offer insights into the moon's geological history and thermal evolution. Such knowledge is crucial for unraveling the enigmatic nature of this celestial body and its hidden depths. Tidal heating emerges as a pivotal factor, contributing to the maintenance of liquid water beneath the icy crust of Europa. The gravitational pull exerted by Jupiter, along with the moon's own eccentric orbit, generates significant tidal forces. This interaction stretches and compresses the icy surface, leading to internal friction that produces heat. The dynamic interplay between these forces creates a warm environment, essential for sustaining liquid water beneath the frozen exterior. Thermal models suggest that sufficient heat can prevent the ocean from freezing solid, allowing it to remain in a liquid state. This phenomenon is not isolated to Europa. It has been observed in other icy moons as well, where tidal heating plays a critical role in their geophysical processes. The warmth generated within this ocean could foster a unique ecosystem, potentially harboring microbial life. Layers of ice above the liquid water serve as both a protective shield and a barrier to exploration. These icy structures may vary in thickness, influencing the heat retention and circulation of nutrients within the ocean. Such variability creates a complex environment that scientists are eager to study further. Understanding the role of tidal heating in maintaining liquid water provides vital insights into the moon's potential habitability. The continued exploration of these hidden oceans remains a priority in astrobiological research, offering tantalizing possibilities for life beyond Earth. Chemical analysis from spacecraft reveals the intricate composition of Europa's ice, a crucial element in understanding the moon's potential for harboring life. Spectroscopic data collected during flybys indicates a surface predominantly composed of water ice, with additional compounds such as magnesium sulfate and sodium chloride These findings suggest a complex interplay of chemical processes occurring beneath the icy crust. The presence of these salts not only points to the possibility of a subsurface ocean, but also implies that this ocean may be chemically active. Such chemical diversity is essential for life, as it provides the necessary building blocks for biological processes. The ice shell itself, estimated to be between 10 to 15 miles thick, acts as a protective barrier, insulating the ocean beneath from the harsh conditions of space, yet allowing for the exchange of materials. Radiation from Jupiter contributes to the surface chemistry, creating a harsh environment that further complicates the potential for life. This unique rhythm of radiation and the resulting chemical reactions may influence the composition of the ocean below, affecting its habitability. Future missions aim to penetrate this thick shell, seeking to directly analyze the ocean's properties and reveal more about its chemical makeup, refining our understanding of Europa's capacity to support life in its hidden depths. Surface chemistry on Europa offers a glimpse into the ocean that lies beneath the icy crust. Spectroscopic studies have detected various salts, such as magnesium sulfate and sodium chloride, scattered across the surface. These compounds suggest a complex interaction between the ocean and the overlying ice. The presence of salts indicates that the ocean may be in contact with rocky materials, which could facilitate chemical reactions essential for life. In addition to salts, organic molecules have also been identified in certain regions. These compounds are the building blocks of life, hinting at the potential for biological processes occurring within the hidden ocean. The distribution of these materials is uneven, with some areas exhibiting a higher concentration, raising questions about the geological processes at play. Cryovolcanism, or ice volcanism, may play a significant role in transporting these compounds from the ocean to the surface. This activity could create pathways for nutrients to cycle through the ice, possibly supporting microbial life within the subsurface layers. Understanding the composition of these surface materials provides critical insight into the ocean's chemistry and its potential habitability. These findings prompt further exploration of Europa's jagged ice, where the interplay of surface and subsurface chemistry continues to intrigue scientists. The search for life, driven by these discoveries, remains a key focus in the ongoing quest to unveil the mysteries of this icy moon. Spectroscopy offers profound insights into Europa's hidden ocean by analyzing the reflected light from its surface. This method reveals the chemical composition of the ice crust, essential for understanding the environment beneath. Variations in light absorption provide clues about the presence of salts, organic compounds, and other elements that might indicate biological activity. The icy shell, with its intricate patterns and varying thickness, interacts with sunlight in ways that can be meticulously studied. Reflectance measurements disclose information about the molecular structure of the surface materials. These signatures allow scientists to infer the composition of the ocean below the ice. The presence of certain compounds, such as magnesium sulfate or sodium chloride, suggests chemical processes that could support life. This region's surface is also marked by signs of geological activity, including ridges and fractures that may allow materials from the ocean to reach the surface, further enriching the potential for habitability. Upcoming missions aim to utilize advanced spectrometers to capture high-resolution spectra, illuminating the details of Europa's icy shell. Understanding the light reflected from this moon could reveal the interactions between the surface and the ocean, offering a glimpse into the potential for life in this subsurface environment. Each spectral fingerprint contributes to a larger picture of a world that remains tantalizingly mysterious. Geological activity on Europa suggests the presence of cryovolcanism, a phenomenon distinct from conventional volcanism. This process involves the eruption of water, ammonia, a phonomate, or other volatile substances, rather than molten rock. Geological observations indicate that the surface is marked by ridges, fractures, and chaotic terrains, hinting at a dynamic subsurface environment. The icy crust may be acting as a shell, covering a liquid ocean beneath. which is subjected to varying pressures and temperatures. Current theories propose that tidal forces exerted by Jupiter create sufficient heat to maintain this subglacial ocean in a liquid state. As the Moon orbits its massive parent, these gravitational interactions cause the ice to flex and crack, allowing the ocean below to influence the surface. Evidence of plumes has been detected, suggesting that materials from this hidden ocean may be venting into space. Such occurrences provide crucial insights into the ocean's composition and the potential chemical signatures of life. The implications of these findings extend beyond mere geological curiosity. Understanding cryovolcanism could reveal how essential elements cycle within this alien environment. The possibility of microbial life, sustained by the chemical energy from hydrothermal vents on the ocean floor, adds an intriguing layer to the exploration of Europa. Each scientific inquiry deepens the understanding of this enigmatic moon and its potential to harbor life. The geological history of Europa is etched in its surface, marked by numerous impact craters that reveal insights into its past. These scars not only indicate the frequency of collisions with celestial bodies, but also suggest a dynamic, evolving environment beneath the icy exterior. Each crater serves as a window into the processes that have shaped this moon, offering clues about its internal structure and the depth of the ocean hidden beneath the thick ice. The distribution and morphology of these craters provide evidence of tectonic activity, suggesting that the ice shell is not static. Instead, it may float atop a subsurface ocean, where heat from the moon's core could create conditions suitable for life. The varying depths of these craters can indicate the thickness of the ice, which is crucial for understanding the potential for nutrient exchange between the ocean and the surface. As researchers analyze the impact sites, they gather data on the composition of the ice and the underlying ocean. The presence of certain elements and compounds could hint at biological processes, further fueling the quest for extraterrestrial life. The intricate relationship between impact events and the ocean's dynamics highlights a complex interplay that continues to intrigue scientists, shaping the narrative of Europa as a prime candidate in the search for life's origins beyond Earth. The Europa Clipper mission represents a significant leap in understanding this enigmatic moon, designed to conduct detailed reconnaissance of Europa's ice shell and subsurface ocean. It aims to uncover the moon's potential habitability. Equipped with a suite of scientific instruments, it will gather invaluable data regarding the moon's composition and geophysical properties. The ice-penetrating radar will probe beneath the thick crust, revealing the depth and salinity of the ocean beneath. This instrument's ability to delineate layers within the ice is essential for determining how nutrients and energy transfer between the ocean and the surface. Spectrometers will analyze the surface composition, identifying organic chemicals and materials that may provide clues about biological processes. Magnetometers will measure the magnetic field surrounding Europa, offering insights into the ocean's conductivity and, by extension, its potential for supporting life. This data will help ascertain the ocean's depth and its interaction with the rocky mantle beneath. Thermal emission radiometers will assess the heat flow from the interior, shedding light on geological activity and the potential for hydrothermal vents, which could serve as habitats for microbial life. Together, these instruments will provide a comprehensive overview of Europa, advancing the quest to understand if life exists in its icy depths. Each observation will contribute to a growing understanding of this captivating world. The dynamics of the subsurface ocean on Europa present an intricate environment shaped by various factors. Beneath the icy crust, this ocean is influenced by tidal heating, which arises from gravitational interactions with Jupiter and its other moons. Such forces create a constant state of flux, allowing for nutrient mixing and thermal gradients essential to potential life forms. Temperature variations within the ocean can lead to diverse chemical processes, offering a range of possibilities for habitability. Hydrothermal vents, akin to those on Earth, may exist on the ocean floor, providing energy sources that support ecosystems. These vents would contribute essential minerals and compounds, fostering a delicate balance between life and its environment. The ice layer above acts as a shield, modulating pressure and isolating the ocean from the harsh radiation of space. This protective barrier plays a crucial role in maintaining the stability of the subsurface conditions. Scientists continue to analyze data from missions studying Europa's surface features, which may offer insights into the ocean below. Understanding the interaction between the ocean and the ice shell is vital for discerning the potential for life. Each discovery expands the knowledge of how this oceanic environment operates, revealing an increasingly complex world hidden beneath a veneer of frost. The conditions beneath the ice may harbor hydrothermal vents, a significant source of potential energy. These geological features, fueled by the moon's internal heat, emerge from the ocean floor, altering the chemistry of the surrounding waters. The heated fluids, rich in minerals, provide an environment that could sustain life. It is within these warm, mineral-laden waters that microbial communities may flourish, thriving in a seemingly inhospitable environment. The presence of such vents indicates that energy sources, similar to those found on Earth, could exist in this hidden ocean. Studies suggest that the interactions between seawater and the rocky mantle may create a variety of chemical compounds, forming the building blocks of life. This dynamic system raises intriguing possibilities regarding the types of organisms that could inhabit Europa's depths. In particular, the potential for chemosynthesis becomes paramount. Organisms utilizing chemical reactions as energy sources could thrive, drawing nutrients from the minerals spewing forth from the seafloor. This method of sustenance contrasts sharply with the reliance on sunlight observed in many terrestrial ecosystems. The exploration of these hydrothermal vents not only illuminates Europa's potential for hosting life, but also provides insight into the fundamental processes that govern oceanic environments, extending the understanding of life's resilience in extreme conditions. The effects of radiation on Europa's surface and ice are significant in understanding its potential habitability. This region is bombarded by intense radiation from Jupiter's magnetic field, which affects both the chemical composition of the surface and the structural integrity of the icy crust. The high-energy particles interact with molecular structures, creating a variety of compounds that may serve as building blocks for life. The radiation penetrates the ice layer, induces changes in the material itself. This process leads to the formation of a layer of oxidants, particularly hydrogen peroxide, which can penetrate deeper into the ice. These compounds may eventually find their way into the subsurface ocean, potentially acting as an energy source for microbial life, should it exist. The ice acts as a shield, yet it also allows for the possibility of chemical exchange between the surface and the ocean beneath. Surface features, such as ridges and chaos terrains, reveal the dynamic interplay of radiation and ice. Cracks and fissures suggest ongoing geological activity, which may facilitate the movement of nutrients and energy from the ocean to the surface. This interaction creates a complex environment where the potential for life, though hidden beneath layers of ice, remains tantalizingly within reach, a reminder of the delicate balance between extremes and existence. The astrobiological significance of this ocean extends far beyond mere speculation. Deep beneath the icy crust, conditions may mirror some of the most extreme environments on Earth, where life thrives in complete darkness. Hydrothermal vents could provide the necessary energy and nutrients, supporting unique ecosystems. These vents, rich in minerals, create an environment reminiscent of those found in the deep sea, where microbial life forms flourish under immense pressure without sunlight. Chemical reactions within these vents may also produce organic compounds essential for life. This process mirrors the theories surrounding the origins of life on our planet, suggesting that life may be a common outcome wherever these conditions are met. Understanding Europa's ocean could offer insights into similar celestial bodies, such as Enceladus and Ganymede, where subsurface oceans might harbor comparable life-sustaining environments. The potential for discovering life in such places raises fundamental questions about the uniqueness of terrestrial organisms. If life exists beyond Earth, it may not conform to our established understanding, pushing the boundaries of biological classification. The study of Europa's ocean challenges scientists to rethink life's resilience and adaptability in the universe. The continued exploration of this hidden ocean remains imperative, as it holds keys to understanding both our origins and the potential for life elsewhere in the cosmos. The future of astrobiology hinges on the knowledge that lies beneath Europa's icy surface. Life in extreme environments on Earth provides crucial insights into the potential for existence beneath Europa's thick ice. Deep-sea hydrothermal vents exemplify conditions that parallel what may be found in the hidden ocean of this moon. Here, organisms thrive in total darkness, relying on chemosynthesis rather than sunlight for energy. The unique ecosystems surrounding these vents challenge traditional notions of habitability, revealing that life can flourish in extreme temperatures and pressures. On the frozen expanses of Antarctica, subglacial lakes harbor microbial life that remains isolated from the outside world for millennia. These resilient organisms survive beneath layers of ice, drawing energy from chemical reactions within their environment. This setting mirrors what scientists speculate might exist beneath Europa's crust, where liquid water, warmth from tidal heating, and essential nutrients could create a viable habitat. Similar adaptations can be seen in the arid conditions of the Atacama Desert, where extremophiles endure significant desiccation and temperature fluctuations. The resilience of such organisms suggests that life may not only exist, but could also adapt to harsh conditions beyond Earth. Research into these analog ecosystems contributes significantly to astrobiological exploration, providing a framework for understanding potential life forms that may inhabit Europa's hidden ocean, waiting to be discovered in the icy silence of the cosmos. Methanogenic microbes, thriving in extreme environments on Earth, serve as a compelling model for potential life forms within Europa's ocean. These microorganisms derive energy from the chemical processes of methane production, demonstrating remarkable adaptability to high-pressure conditions and low temperatures. Such resilience raises intriguing possibilities regarding similar life forms that could inhabit the subsurface ocean beneath Europa's icy crust. This ocean, shielded from the harsh radiation of space, may harbor a rich chemistry that supports the metabolic pathways of methanogens. Hydrothermal vents on ocean floors, where heated mineral-rich water emerges, could serve as energy sources analogous to those found on our own planet. Such environments provide the warmth and nutrients necessary for microbial life to flourish, creating ecosystems that could sustain complex biological interactions. The icy shell above acts as a protective barrier, maintaining a stable environment beneath her, where temperature and pressure conditions are conducive to life. The discovery of organic compounds on Europa's surface further enhances the intrigue surrounding its potential for life. In this context, the ongoing exploration of the Moon's surface and subsurface, through missions designed to penetrate the ice, will be critical. Each finding adds depth to our understanding of the conditions that may enable methanogenic microbes to exist, illuminating the broader search for life in our solar system. The search for organic compounds is essential in understanding the potential for life beneath Europa's icy crust. This region, characterized by a thick layer of water ice, conceals what is believed to be a vast ocean, rich in the chemical ingredients necessary for biological processes. Investigations have revealed that the surface is strewn with various materials, hinting at the complex interactions taking place beneath. Spectroscopic analyses conducted by spacecraft have detected the presence of simple organic molecules, such as carbon dioxide and methane. These compounds serve as potential building blocks, forming the foundation upon which life could emerge. The dynamics of these organic materials are influenced by the Moon's unique geological activity, which may facilitate the synthesis of more complex organic structures. In addition, the potential for hydrothermal vents on the ocean floor is of particular interest. Such environments could provide both the heat and chemical gradients necessary for sustaining microbial life. These vents, similar to those found on Earth, might create localized ecosystems, allowing life to thrive in isolation. Understanding the distribution and concentration of these organic compounds enhances the knowledge of Europa's habitability. As missions continue to gather data, scientists remain focused on deciphering the intricate chemistry that could support life within this enigmatic ocean world. This ice layer presents significant challenges for any potential life forms striving to emerge in Europa's hidden ocean. Its thickness varies, sometimes reaching depths of several kilometers, creating a formidable barrier between the surface and the vast liquid expanse beneath. This substantial insulation affects not only thermal dynamics, but also the availability of essential nutrients and energy sources. The icy crust acts as a shield against cosmic radiation and other environmental hazards, yet it also limits the potential exchange of materials. The ice's composition can complicate the transfer of organic compounds, which are critical for biological processes. Any life forms that manage to exist in this dark, pressurized environment would need to adapt to extreme conditions, including high salinity and low temperatures. Beneath this frozen exterior, chemical reactions may occur, driven by geothermal heat from the Moon's interior, which could provide a potential energy source. Yet, the isolation imposed by the ice layer raises questions about the viability of sustaining complex ecosystems. An intricate interplay of factors, including the stability of the ice, geothermal activity, and chemical availability, remains crucial in understanding whether life could not only emerge but also thrive in such a unique environment. The ongoing exploration aims to unravel these complexities, bringing insights into the potential for life beyond Earth. The surface of Europa presents significant challenges to sampling efforts. This icy shell, composed primarily of water ice, varies in thickness, ranging from several kilometers to potentially tens of kilometers. The integrity of this frozen crust is essential to understanding what lies beneath. Cracks and ridges, formed by the Moon's tidal forces, complicate access, leading to uncertainties about the stability of the surface. Mechanical and thermal properties of the ice present additional hurdles. Extreme temperatures, often plummeting to -160 degrees Celsius, hinder the functionality of instruments designed to penetrate the surface. The ice may also exhibit a complex layering, where briny water, formed by interactions with the Moon's rocky mantle, could be trapped beneath, influencing sampling techniques. Radiation levels in this environment are another consideration. Europa orbits within a strong magnetic field, exposing its surface to intense radiation from Jupiter. This factor not only affects the durability of equipment, but also poses risks to any organic compounds that might be present. The skills to overcome these obstacles include advanced robotic systems designed for ice drilling and autonomous navigation. Collaborative international missions aim to assess the viability of these technologies. Each attempt to sample Europa's surface is a step towards understanding its enigmatic subsurface ocean and the potential for life within it. Future missions aim to further explore this intriguing moon, focusing on the development of specialized landers and rovers designed to traverse its icy crust. These proposals emphasize advanced technologies capable of penetrating the thick, frozen shell that conceals the ocean beneath. Equipped with drills and analytical instruments, landers could extract samples from various depths, revealing the composition of the ice and the chemistry beneath. Rovers, with their mobility, would enable extensive surveys of the surface, investigating geological features and potential cryovolcanism, which may provide clues about the ocean's dynamics. By analyzing the interaction between the surface and subsurface environments, scientists could gain insights into the habitability of this hidden ocean. Proposals include the use of autonomous systems capable of navigating the harsh conditions, where radiation levels and extreme temperatures challenge even the most robust designs. These missions also consider the potential for in-situ resource utilization, allowing for the extraction of energy and materials from the environment. The detailed data collected would not only enhance knowledge of Europa, but also inform future explorations of icy worlds beyond our solar system. Each successful mission gradually builds a comprehensive understanding of this dynamic region, illuminating the possibilities for life in environments once thought uninhabitable. The search continues, with each task revealing more about the mysteries of the cosmos. Planetary protection plays a crucial role in the exploration of Europa, a celestial body that holds the potential for life within its hidden ocean. This region demands meticulous attention to ensure that Earth microbes do not contaminate its delicate environment. The icy surface, which conceals a vast ocean beneath, is a prime candidate for astrobiological research. Yet safeguarding its pristine conditions is paramount. Protocols are set in place to sterilize spacecraft and instruments before their launch, reducing the risk of inadvertently introducing terrestrial life. The complexities of this undertaking are profound, as even the smallest particles can have significant consequences on the integrity of Europa's ecosystem. Precautions extend to the design of missions, requiring innovative engineering solutions that align with these protective measures. Vigilance continues throughout the mission lifecycle, from launch to landing. Teams monitor and document every aspect of the spacecraft's journey, ensuring adherence to strict guidelines. The hope is that exploration will yield insights into Europa's subsurface ocean and its potential habitability, while maintaining the integrity of this enigmatic moon. This approach reflects a growing understanding of the interconnectedness of life across the solar system. The delicate balance between exploration and preservation shapes the future of astrobiology, guiding humanity toward responsible scientific engagement with other worlds. Studying Europa from orbit reveals the complexities of its icy exterior and the secrets concealed beneath. Remote sensing techniques allow scientists to gather critical data regarding surface composition, thermal characteristics, and topographical features. These observations contribute to an understanding of the Moon's geological history and current processes, all without direct contact. Spectroscopy provides insights into the composition of Europa's surface, identifying key materials such as water ice and salt deposits. Variations in spectral signatures suggest the presence of organic molecules, hinting at the potential for life. Thermal imaging unveils the temperature distribution across the Moon's surface, revealing areas where heat is escaping, possibly indicating active geological processes or subsurface oceanic dynamics. Topographical analysis, achieved through radar and altimetry, maps the Moon's icy crust, exposing ridges, fractures, and chaotic terrain. These features may be indicative of tectonic activity, suggesting that the ocean beneath is not merely stagnant, but is, in fact, dynamic. The interplay between these elements can provide a clearer picture of the Moon's habitability. The accumulation of this data is vital for informing future missions aimed at direct exploration. Understanding the subtleties of Europa's environment through remote sensing allows scientists to develop targeted hypotheses regarding its potential to harbor life. Each observation deepens the connection between this celestial body and the broader quest to understand life's existence beyond Earth. Astrobiology serves as a crucial framework for exploring the potential for life in extreme environments, such as those found beneath icy crusts. In this context, it investigates the conditions necessary for life to thrive, encompassing factors like temperature, pressure, and chemical availability. This field gathers insights from terrestrial extremophiles, organisms capable of surviving in harsh conditions on Earth. Research into these organisms reveals how life might adapt to the frigid, high-pressure environment of Europa's subsurface ocean. The presence of liquid water is a fundamental criterion for habitability. Yet it is the composition of that water, enriched with elements such as carbon and sulfur, which may further enhance its suitability as a cradle for life. Ongoing studies focus on the Moon's surface, where measurements of its icy shell provide hints about what lies beneath. These analyses allow scientists to infer the chemistry of the underwater environment. Models based on data from similar environments on Earth, such as hydrothermal vents or subglacial lakes, help assess the likelihood of biological processes occurring in Europa's ocean. Each finding contributes to a broader understanding of where life may emerge in the universe, reflecting the intricate interplay between environmental conditions and biological potential. The quest remains rooted in the examination of these icy realms, as researchers continue their meticulous search for signs of life. Equally, all implications regarding Europa extend beyond its icy surface, influencing the broader understanding of habitability within the solar system. Conditions on this moon suggest the presence of a subsurface ocean, which raises questions about the chemical interactions occurring beneath the ice. This environment may mirror ancient Earth, where life first emerged in deep-sea hydrothermal vents, allowing scientists to speculate on the potential for extraterrestrial organisms. The presence of a salty ocean, combined with the underlying heat generated by tidal forces, creates a unique environment. Salinity and temperature gradients promote chemical reactions that could support life. This region, with its robust potential for energy sources, places Europa alongside other celestial bodies, such as Enceladus and Mars, in the search for extraterrestrial ecosystems. Comparative analysis of these worlds reveals a pattern. Many icy moons and planets exhibit similar features. The potential for liquid water beneath the surface is a unifying factor, leading to hypotheses regarding life's adaptability in extreme conditions. Europa's geophysical characteristics contribute significantly to the understanding of habitability, suggesting that life may exist in unexpected places throughout the solar system. These findings compel further exploration, with future missions aimed at unraveling Europa's secrets, potentially reshaping our comprehension of life beyond Earth. The implications of such discoveries resonate through scientific inquiry into the origins and prevalence of life in the cosmos. The exploration of Europa prompts comparisons with other ocean worlds within the outer solar system. Enceladus, a moon of Saturn, reveals its subsurface ocean through plumes of water vapor escaping from its south polar region. These geysers, rich in organic compounds, suggest an environment where life could potentially thrive. The presence of a liquid ocean beneath a thick, icy crust mirrors Europa's characteristics, indicating that multiple celestial bodies may harbor similar conditions. Titan, Saturn's largest moon, presents a unique case. Its surface hosts rivers and lakes of liquid methane and ethane, while a subsurface ocean of water and ammonia lies beneath its frigid exterior. This complex chemistry raises intriguing possibilities for life that is fundamentally different from that on Earth. The diverse environments of these ocean worlds highlight various pathways for potential habitability. Each of these moons presents a distinct set of conditions, yet they share a common theme: the presence of liquid, which is essential for the chemistry of life. The study of these celestial bodies contributes to an evolving understanding of where life might exist beyond Earth. As missions advance, the comparative analysis of their geological and chemical characteristics will deepen insights into the potential for life in the universe, expanding the search beyond familiar terrestrial environments. Ice dynamics play a crucial role in understanding the relationship between the ice shell and the subsurface ocean on Europa. This icy crust, believed to be several kilometers thick, insulates the ocean beneath, maintaining its liquid state. Despite the frigid conditions of the surface, variations in thickness and temperature within this shell can create a complex interplay of forces influencing both the ocean's chemistry and potential habitability. Tidal heating, generated by gravitational interactions with Jupiter, contributes to the maintenance of liquid water beneath the ice. As the ice shell flexes with these tidal forces, it may crack and shift, allowing nutrient exchange between the ocean and the overlying ice. This process is essential for sustaining any potential life forms that may exist in the dark depths below. Crucial to the ongoing study are the observed surface features, including ridges and chaos terrains, which provide clues about the ice shell's movement and deformation. These formations suggest that the ice is not static but rather dynamic, responding to the underlying ocean's motions and thermal conditions. Understanding these interactions enhances knowledge of how energy and materials cycle within Europa's system. In turn, these insights deepen the comprehension of how similar processes may occur on other icy moons and exoplanets, broadening the scope of astrobiological possibilities. The potential for life hinges on several fundamental requirements and conditions, each intricately linked to the environment beneath the icy surface. Liquid water emerges as a primary necessity, serving as a solvent for biochemical reactions essential for life as understood on Earth. This subsurface ocean, kept warm by tidal heating and radioactive decay, offers a stable environment where organic compounds can thrive. Chemical energy sources play a crucial role in sustaining life in such extreme conditions. Hydrothermal vents, similar to those found on Earth's ocean floor, may provide the necessary nutrients and energy. These vents can create localized habitats where microorganisms can flourish, suggesting that life could exist in the darkness beneath thick ice. Radiation levels on the surface present a significant challenge, yet they also underscore the adaptability of potential life forms. Some extremophiles on Earth endure high radiation levels, indicating resilience and the ability to survive in harsh environments. This adaptability raises the possibility that life on Europa could utilize alternative biochemical pathways, distinct from those familiar to researchers. The presence of organic molecules detected by missions such as Galileo further supports the hypothesis. These compounds could serve as building blocks for life, enhancing the prospect of biological processes occurring within the hidden ocean, where conditions may vary widely yet remain conducive to the emergence of life. The complexities of this undertaking are profound. The interaction between the icy crust and the liquid water below can facilitate the exchange of essential elements. This region likely experiences hydrothermal activity, where heated water interacts with the surrounding rock. Such interactions may release minerals and nutrients that are crucial for biological processes. Organic compounds, formed either from extraterrestrial sources or synthesized under the ice, can serve as energy sources. These compounds can undergo complex chemical transformations, driven by microbial life, or through abiotic processes. The presence of sulfur, nitrogen, and phosphorus compounds suggests a rich geochemical environment that could sustain life. Various physical and chemical gradients exist within the ocean, creating distinct ecological niches. The thermal gradient near hydrothermal vents could lead to localized zones of high productivity. Conversely, the colder, darker regions further from these heat sources may harbor different metabolic pathways. These nutrient-rich areas may support microbial communities that utilize chemosynthesis instead of photosynthesis, deriving energy from inorganic compounds rather than sunlight. Such adaptations would allow these organisms to thrive in environments that are otherwise inhospitable. The potential for life in these hidden ecosystems underscores the importance of exploring this enigmatic moon and understanding its geochemical dynamics. The influence of Jupiter's immense gravity plays a critical role in shaping the environment on Europa. This colossal gas giant generates significant tidal forces, which induce stress and strain upon the icy crust. These effects lead to fluctuations in the thickness of the ice, creating cracks and fissures that may allow for the exchange of materials between the surface and the underlying ocean. This interaction generates a dynamic system where energy is transferred from the moon's core to its ocean, potentially creating a warm, chemically rich environment. It is within these depths that conditions may become conducive to life. The continuous movement of the ice above acts as a protective layer, shielding the ocean from harmful radiation while maintaining a stable environment. The tidal heating effect is not uniform. Variations across Europa's surface lead to localized areas of heightened geological activity. This may result in plumes of water vapor that erupt through the ice, contributing to the moon's thin atmosphere. Such phenomena are of great interest to scientists, as they offer a glimpse into the composition of the subsurface ocean. Understanding these tidal dynamics is essential for assessing the moon's habitability. The interplay between gravitational forces and geological processes creates a complex and intriguing setting that challenges our perceptions of life beyond Earth. Cosmic rays, high-energy particles originating from various astrophysical sources, continually bombard the surface of Europa. This relentless influx contributes to the moon's unique and dynamic environment. The icy crust absorbs these particles, leading to the creation of a diverse array of chemical compounds. These interactions result in the alteration of surface materials, generating a variety of complex organics that may play a role in potential biological processes beneath the ice. The radiation from cosmic rays also induces structural changes in the ice, fracturing the surface and allowing for potential exchange between the subsurface ocean and the external environment. This phenomenon creates a network of fissures and ridges, which may facilitate the transport of nutrients and energy sources crucial for sustaining life. The effects of these cosmic phenomena are not merely superficial. They penetrate into the icy shell, influencing the physical and chemical properties of the ice layers. The interplay of temperature fluctuations, radiation exposure, and geological activity fosters a dynamic atmosphere that can support a variety of chemical pathways. Understanding the impact of cosmic rays on this moon is vital for assessing its habitability. Such knowledge not only illuminates the ongoing processes shaping Europa, but also enhances our comprehension of where life might emerge in the universe. Geological timescales reveal a complex history of Europa, marked by a dynamic interplay of tectonic activity and cryovolcanism. The surface, characterized by its intricate network of ridges and grooves, indicates a once active environment subject to the forces of internal heating. This heat likely originates from tidal flexing caused by gravitational interactions with Jupiter and its other moons, creating an ongoing cycle of geological transformation. The icy shell, which can be several kilometers thick, acts as a protective barrier over the subsurface ocean. Over millions of years, the gradual resurfacing of this ice suggests a recycling process. as older materials are replaced by newer formations. These geological processes contribute to a diverse range of surface features, including chaotic terrains where ice has broken apart and reassembled. Underneath the shell, the hidden ocean may harbor a rich and complex ecosystem, potentially sustained by chemical reactions between the ocean and the rocky seafloor. Variations in salinity and temperature within this ocean could further influence the chemical dynamics, leading to localized environments conducive to life. Understanding these geological processes not only informs scientists about Europa's past, but also provides insights into its current conditions and the potential for biosignatures residing within its depths. Europa's atmosphere presents a thin yet intriguing layer of various gases, primarily composed of oxygen. This tenuous envelope, measuring approximately 100 kilometers in height, exhibits a pressure around 100 billionth of that found on Earth. The presence of molecular oxygen suggests ongoing processes, possibly driven by radiation and surface interactions. Ultraviolet radiation from Jupiter's intense magnetic field interacts with the Moon's icy surface, facilitating the transformation of water molecules. Resulting chemical reactions create a stark contrast between the surface and the underlying ocean, raising questions about their interconnectedness. The thin atmosphere does not offer significant shielding from radiation, yet it may play a role in the potential habitability of the hidden ocean below. Surface features, such as ridges and cracks, hint at a dynamic geological history, influenced by the ocean beneath. These characteristics might also reveal the processes that shape the atmosphere itself. Variations in surface temperature and composition influence the distribution of gases, hinting at underlying activity. The detection of trace amounts of complex organic molecules within this atmosphere adds another layer of complexity to Europa's environment. Ongoing observations and future missions may shed light on the intricate interplay between the surface and subsurface, potentially guiding the search for life within this enigmatic moon. Community science has emerged as a significant force in astrobiological research, particularly when exploring distant celestial bodies like Europa. Enthusiasts and amateur astronomers contribute valuable data, often leveraging accessible technologies to monitor and analyze celestial phenomena. These contributions can enhance the scope of professional investigations, providing a wider array of observations that might otherwise go unnoticed. Many projects invite public participation in data collection, fostering a sense of shared purpose. As individuals engage with the mysteries of the cosmos, they often develop innovative techniques to interface with complex datasets. Collaborative platforms allow for the aggregation of findings, creating a rich reservoir of information that researchers can draw from when studying potential biosignatures. The integration of community science into astrobiology encourages a diverse range of perspectives, enriching the discourse surrounding the search for extraterrestrial life. This democratization of science not only expands the research community, but also inspires curiosity about the universe. The potential for new discoveries increases as participants share insights and methodologies, furthering the understanding of environments that might harbor life. As advancements in technology continue to lower barriers to entry, the involvement of dedicated individuals ensures that the exploration of Europa and similar worlds remains vibrant and dynamic, reinforcing the notion that the quest for knowledge transcends professional boundaries. Previous missions have provided invaluable insights into the nature of Europa's icy shell and the subsurface ocean lurking beneath. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, captured detailed images of this moon's surface. These observations revealed a complex interplay of ridges, cracks, and chaotic terrain, suggesting geological activity that could indicate an interaction between the ocean beneath and the icy crust above. Following Galileo, the Hubble Space Telescope observed plumes of water vapor erupting from the Moon's surface, hinting at the possibility of a more dynamic environment than previously understood. These findings prompted further analysis, leading scientists to consider the implications of a potentially habitable ocean beneath the thick ice. The presence of salts and other compounds detected on the surface raised questions about the chemistry that could support life. Lessons from these missions emphasized the importance of multidisciplinary approaches, combining data from various sources, including spectroscopic analysis and thermal imaging. Understanding the composition of the ice and the ocean beneath is crucial for identifying potential biosignatures. Each piece of evidence builds a more comprehensive picture of this moon, revealing the delicate balance of conditions that may foster life. The cumulative knowledge gained shapes future missions, guiding the design of instruments meant to penetrate the icy crust and explore the subsurface world directly. The prospect of human exploration on Europa emerges as a tantalizing possibility. Its enigmatic surface, characterized by a fracturing ice shell, hints at a dynamic environment beneath this hidden ocean, potentially teeming with life. Remains one of the most compelling targets in the solar system. Advanced technologies will be required to navigate the harsh conditions present on this moon. Robotic scouts may first pave the way, assessing the stability of the ice and identifying regions where penetrative drilling could yield access to the ocean beneath. Surface temperatures hover around -150 degrees Celsius, presenting formidable challenges for human explorers. Protective habitats will need to be established, capable of withstanding extreme cold while providing essential life support. The development of sustainable energy sources will play a crucial role as solar power diminishes under thick ice and the faint sunlight that reaches this distant world. Life detection missions will prioritize understanding the chemical composition of the subsurface ocean, searching for biosignatures that could indicate biological activity. The implications of such discoveries extend beyond planetary science, offering insights into the resilience of life in extreme environments. This moon serves as a microcosm for astrobiological questions, linking the potential for life on other celestial bodies with humanity's quest to explore the universe. The exploration of Europa raises complex ethical questions intertwined with the pursuit of astrobiology. The potential discovery of life beneath its icy crust necessitates a careful examination of humanity's role as an interloper in these pristine environments. This region, untouched for billions of years, invites contemplation on the implications of human interference. Scientific protocols must be established to mitigate contamination risks that could jeopardize native ecosystems should they exist. The introduction of terrestrial microorganisms poses a significant threat to undiscovered life forms, underscoring the responsibility to preserve their habitats. Ethical frameworks must guide researchers, ensuring that the quest for knowledge does not come at the expense of other worlds' intrinsic value. The morality of prioritizing human curiosity against the sanctity of extraterrestrial life forms requires a delicate balance. Each decision made during missions influences not only the immediate scientific landscape, but also the broader implications for future exploration. In this delicate interplay, the potential for life on Europa challenges prevailing attitudes towards exploration. As humanity gazes into the vastness of space, the ethical considerations surrounding the search for life serve as a reminder of the shared responsibility to protect the universe's mysteries. The continued dialogue around these moral questions shapes the future of astrobiological endeavors, guiding humanity's interactions with the cosmos. The integration of artificial intelligence and machine learning into the analysis of data marks a significant evolution in astrobiological research. These advanced technologies possess the capacity to process vast amounts of information with remarkable efficiency, enabling scientists to derive insights from the complex datasets associated with Europa's icy surface and potential subsurface ocean. Algorithms can identify patterns and anomalies within the data, revealing hidden structures beneath the thick layer of ice. This capability allows for the detection of potential hydrothermal activity, which could foster the development of life. The precision of machine learning enhances the interpretation of spectral data, facilitating the identification of chemical compounds that are indicative of biological processes. In this environment, AI can assist in correlating findings from various sources, such as satellite imagery and ground-based observations, to create a more comprehensive understanding of the Moon's geology and potential habitability. The ability to simulate various conditions within the ocean expands the scope of exploration, allowing researchers to predict how life might adapt to the extreme environments beneath the ice. With the ongoing advancements in these technologies, the quest to uncover the secrets of Europa's hidden ocean is becoming increasingly feasible. The collaboration between human intuition and machine learning paves the way for groundbreaking discoveries in the search for extraterrestrial life. The theoretical acoustics of subsurface oceans provide a compelling insight into the depths of Europa beneath its icy crust. The ocean likely harbors unique soundscapes created by the interaction of water with the underlying geology. These sound waves travel through the liquid medium, reflecting off features such as ridges and thermal vents. The temperature and pressure differences contribute to a complex acoustic environment where frequencies can vary dramatically. In this environment, researchers speculate that the sounds produced may reveal the characteristics of the ocean itself, including its salinity, density, and potential biological activity. The presence of life may generate distinct acoustic signatures, which could be detected by future missions. Analyzing these sound patterns could offer invaluable information about the ocean's conditions and the possibility of microbial ecosystems thriving in isolation. Under the vast, frozen surface, the sounds of water dynamics become an essential tool for exploration. The potential for ice cracking and shifting adds another layer to the acoustic profile, creating a rhythmic pulse that may hint at geological activity. This region of Europa remains a place of intrigue where sound waves serve as messengers, conveying stories of a hidden world beneath the ice, waiting to be understood and explored. The pursuit of these auditory signals continues to guide scientific inquiry into the depths of this enigmatic moon. Understanding the physics of ice movement reveals critical insights into the dynamics of Europa's surface. The icy crust, which can be several kilometers thick, behaves as a complex system subject to various forces. These forces include tidal heating, driven by the gravitational pull of Jupiter and its other moons. This interaction creates stress within the ice, resulting in fracturing and the movement of massive ice plates. Studies indicate that the ice may exhibit a fascinating ability to shift, create new formations, and close gaps. The process of strain accumulation and release contributes to the surface's irregularities and features, such as ridges and chaos terrain. These deformations hint at a subsurface ocean where conditions may foster life. Measurements of surface temperature fluctuations provide additional data regarding the ice's behavior. Variations can indicate the thickness of the crust and its thermal properties, essential for understanding potential oceanic conditions beneath the pulse. Computer models simulate these dynamics, offering predictions on how ice movement may evolve over time. In turn, this assists in interpreting the geological history of this region, suggesting cycles of freeze and thaw that might connect with the ocean beneath. The interplay of forces shaping the ice surface paints a picture of an intricate environment, one that may harbor secrets waiting to be uncovered beneath its frozen exterior. Thermal dynamics play a crucial role in maintaining the hidden ocean beneath Europa's icy crust. This ocean, lying beneath several kilometers of ice, exists in a delicate balance maintained by heat generated from tidal forces. The gravitational pull from Jupiter, combined with the Moon's elliptical orbit, creates friction within the interior. This friction generates heat, which is essential for the preservation of liquid water beneath the ice. Temperature variations across Europa's surface reveal patterns influenced by both the ocean below and the ice above. Certain regions exhibit warmer areas where heat escapes, leading to the formation of warmer, softer ice. These anomalies hint at potential upwellings from the ocean, contributing to the dynamics of ice movement. This interaction not only shapes the surface features, but also suggests that the ocean is in contact with the icy shell, allowing for the exchange of materials. The ocean itself is believed to be rich in chemicals, potentially providing the necessary ingredients for life. Hydrothermal vents, akin to those found on Earth, may exist along the ocean floor, offering a stable energy source. These environments could foster microbial life, thriving in conditions similar to those at the bottom of Earth's oceans. Understanding these thermal processes is essential for evaluating Europa's potential to support life and the overall habitability of icy worlds within the solar system. The history of water on Europa is a complex saga that traces back to the Moon's formation. Initially, the icy surface formed from the accumulation of water ice and silicate materials, creating a crust that obscured the ocean beneath. Over millions of years, the interplay of geological and thermal processes shaped this environment. Tidal forces exerted by Jupiter's immense gravity generated heat, contributing to the maintenance of a subsurface ocean. Geological activity has played a significant role in the evolution of this hidden ocean. Evidence of surface features, such as ridges and chaotic terrain, suggests that materials from the ocean are periodically expelled onto the surface. These processes indicate that the ocean may be in direct contact with the rocky mantle, facilitating chemical interactions that are vital for potential life. At present, the ocean beneath the ice is believed to be in a liquid state, insulated by the thick, icy shell above. This layer varies in thickness, with estimates suggesting it may reach depths of up to 100 kilometers. The presence of salts and minerals within the ocean further enhances its potential for habitability, providing a chemical environment conducive to life. Understanding this history allows scientists to better evaluate the Moon's capacity to harbor life and illuminates the potential similarities shared by other celestial bodies within the solar system. Collaboration in space exploration fosters a shared understanding of complex systems like those found on Europa. Diverse scientific backgrounds contribute to a more comprehensive approach to studying such environments. This pooling of resources and expertise enhances the ability to design missions capable of probing beneath the icy crust. International partnerships enable the sharing of technology, allowing for advancements that a single entity may struggle to achieve independently. Research institutions and space agencies across the globe unite to synthesize data, analyze samples, and validate findings. This synergy leads to innovative solutions for challenges such as the harsh conditions of outer space and the intricate logistics of distant missions. By working together, scientists maximize their potential to uncover the mysteries of celestial bodies, including those that may harbor extraterrestrial life. RATE missions not only reduce costs but also increase the scientific return on investment. The combination of instruments and methodologies from various teams enhances the breadth of exploration. This collective effort ensures that the quest to understand Europa's hidden ocean is informed by multiple perspectives, leading to richer insights. As new technologies emerge and knowledge expands, collaborative frameworks will remain essential. They will pave the way for future explorations, establishing a foundation for the ongoing pursuit of life beyond Earth. Each discovery builds upon the last, reinforcing the interconnected nature of our solar system's exploration. While gravitational interactions between Europa, Io, and Ganymede create a complex orbital resonance, a dance of celestial bodies maintaining stability while influencing each other's trajectories. This relationship is noteworthy, as the pull of these moons generates heat within Europa. Tidal forces result in friction, which may play a significant role in maintaining the subsurface ocean beneath its icy crust. Observations reveal that Europa's orbit is slightly elliptical, a deviation that varies in response to the gravitational influences exerted by its larger companions. This motion creates a dynamic environment with potential variations in pressure and temperature beneath the ice. The resulting geological activity suggests the possibility of nutrient-rich environments which could be conducive to life. The resonance is not merely a mechanical phenomenon, it has implications for understanding the broader dynamics of the Jovian system. The interactions reveal insights into the history of these moons and the evolution of their surfaces. Surface features, such as ridges and cracks, indicate a geological history shaped by these gravitational forces. Continued study of Europa's orbit in relation to Io and Ganymede highlights the importance of these interactions in planetary science. Each observation sheds light on the potential for habitability, reinforcing the significance of this region in the ongoing search for extraterrestrial life within our solar system. Vonkensokolor Fort's wider system. This exploration of habitability extends into the realm of exobiology, a field dedicated to understanding the potential for life beyond Earth. Investigations into extreme environments on our planet serve as a foundation for these scientific inquiries. Organisms thriving in conditions of high radiation, acidity, and extreme temperatures provide valuable insights into the adaptability of life. Such resilience suggests that life could exist in similarly inhospitable environments elsewhere in the cosmos. Astrobiologists focus on identifying biosignatures, elements or compounds indicative of biological activity. These include gases such as methane and oxygen, which, when detected in the atmospheres of distant exoplanets, may suggest the presence of life. The methods employed to study these distant worlds involve sophisticated telescopes capable of analyzing light spectra, offering clues about their atmospheric compositions. The search for extraterrestrial life also encompasses the study of celestial bodies within our own solar system, such as Mars and Enceladus. Each of these locations presents unique environments where microbial life might exist. The potential for subsurface oceans, coupled with the chemical building blocks of life found within these celestial bodies, fuels ongoing research and missions aimed at uncovering the mysteries of life beyond our planet. Scientific advancements continue to refine our understanding of the parameters required for life, guiding future explorations in the vast, uncharted reaches of the universe. Uncharted reaches of the universe. Explorations of Europa's hidden ocean suggest intriguing biochemical pathways that may support life. The ocean, insulated beneath a thick layer of ice, presents a unique environment where chemical reactions could occur in relative isolation from cosmic radiation. Hydrothermal vents on the ocean floor may provide the necessary energy and nutrients, resembling conditions found in Earth's deepest oceans. Complex organic molecules, such as amino acids and hydrocarbons, have been detected on Europa's surface. These compounds indicate that essential ingredients for life exist nearby. The interaction between the ocean and the icy crust could facilitate the transport of these organic materials, creating an environment rich in potential biochemistry. Under specific conditions, it's conceivable that simple life forms could emerge, relying on chemosynthesis rather than photosynthesis for energy. This adaptation would allow organisms to thrive in total darkness, utilizing the chemical energy from minerals released by hydrothermal activity. Laboratory simulations further support the possibility of life in such extreme conditions, showcasing resilience and adaptability among extremophiles on Earth. As missions like the Europa Clipper prepare to investigate these environments, the focus remains on identifying signatures of life, chemical pathways, and understanding how life could evolve in isolation. Each discovery brings humanity closer to answering profound questions about existence beyond Earth. Sample return missions play a crucial role in the quest to understand extraterrestrial environments. They provide the means to gather materials from celestial bodies, offering insights that cannot be fully obtained through remote sensing alone. The complexities of assessing chemical compositions and potential biosignatures are best explored through direct analysis in terrestrial laboratories. This approach allows scientists to employ advanced techniques, revealing the intricate details of organic compounds and mineral formations. These missions facilitate the examination of specific locales where conditions may harbor life or its precursors. For instance, analyzing subsurface ice from Europa could uncover organic molecules or microbial life forms, transforming our understanding of habitability in icy worlds. The return of samples from such destinations ensures that the data is processed using the latest technologies, which may not have been available at the time of collection. This dynamic aspect of research allows for continuous refinement of theories and models about life's potential beyond our planet. Furthermore, these missions foster international collaboration, uniting various space agencies and scientific communities in pursuit of common goals. The shared knowledge gained from returned samples contributes to the broader narrative of astrobiology. Public interest in space exploration has surged, particularly in the quest to understand celestial bodies like Europa. This moon, with its icy surface concealing a vast ocean beneath, ignites curiosity about the possibility of life beyond Earth. Enthusiasm for such discoveries has encouraged funding from both governmental and private sectors. The allure of revealing hidden ecosystems in alien environments fuels debates in scientific circles and captivates the imagination of the public. Investment in missions targeting Europa is driven by a combination of scientific ambition and the potential for groundbreaking discoveries. Funding agencies recognize that unlocking the secrets of this icy moon could answer fundamental questions about the origins of life. This pursuit fosters collaborations among universities, research institutions, and space agencies, amplifying the impact of shared knowledge. The growing interest is reflected in educational programs and outreach initiatives aimed at engaging communities in the exploration narrative. Engaging the public not only enhances awareness, but also encourages the next generation of scientists and engineers. Such enthusiasm permeates the scientific community, fueled by collaborative efforts that transcend borders. International partnerships play a crucial role in advancing the exploration of celestial bodies like Europa. These alliances bring together diverse expertise, resources, and technologies, creating a collective approach to uncovering the mysteries of the universe. Fulminating the scientific rigor behind missions, Instruments developed across continents often find common purpose in these endeavors. For instance, sophisticated imaging systems and spectrometers are designed with contributions from multiple nations, ensuring a comprehensive analysis of potential habitats beneath the ice. Logistical challenges are often mitigated through these collaborations as nations coordinate launches, share data, and optimize mission timelines. The integration of different engineering practices enhances the resilience and adaptability of spacecraft, allowing them to withstand the harsh conditions of outer space. Data sharing accelerates discoveries, with findings from one mission informing the next. This interconnectedness not only fosters innovation, but also nurtures a sense of global responsibility in the quest for understanding life beyond Earth. As humanity's gaze remains fixed on the icy surface of Europa, the combined efforts of international teams exemplify the power of unity in the pursuit of knowledge, bringing us closer to answering profound questions about life in our solar system. Theoretical models of Europa's ocean circulation provide insight into the complex dynamics of this subsurface environment. These simulations suggest that the ocean may be in constant motion, driven by tidal forces exerted by Jupiter's gravitational pull. Such forces induce significant flexing of the icy shell above, resulting in varying pressures that could lead to nutrient-rich upwellings from the ocean floor. Temperature gradients play a crucial role in this circulation. The heat generated by tidal heating is believed to maintain a stable liquid environment beneath the ice, creating conditions conducive to the presence of life. Areas of warmer water may rise, creating currents that transport essential minerals and energy sources throughout the ocean. The thermal dynamics potentially establish a rich ecosystem, with hydrothermal vents acting as a focal point for chemical reactions necessary for life. The ice shell itself may be far from uniform. Variations in thickness could influence the exchange of materials between the ocean and the overlying ice, affecting both circulation patterns and the chemistry of the water. Regions where the ice is thinner might allow for more direct interaction with the ocean, potentially leading to localized habitats that support microbial life. These models, while theoretical, offer a glimpse into the intriguing possibilities that lie beneath Europa's surface, revealing a world that may harbor secrets of life. The conditions on Europa are governed by a complex interplay of factors. The surface is characterized by a cold, icy crust, with temperatures averaging around -150 degrees Celsius. This extreme climate creates a stark contrast with the potential warmth of the hidden ocean below. The thickness of the ice varies significantly, influenced by geological activity and the Moon's tidal heating from its interaction with Jupiter's immense gravitational pull. Weather patterns on Europa are subtle yet compelling. The lack of a substantial atmosphere means that any atmospheric phenomena are markedly different from those on Earth. Thin wisps of gas, primarily composed of oxygen, exist above the surface but do not support weather systems as experienced on terrestrial planets. Instead, the interaction between the surface and the Moon's subsurface ocean generates localized variations, possibly leading to plumes of water vapor that escape through fissures in the ice. These plumes, once detected, suggested that material from the ocean might be expelled into space, providing valuable insights into the ocean's composition. The potential for such geysers indicates that the hidden ocean may be in constant communication with the surface, allowing for an exchange of chemicals that could be essential for life. Understanding these phenomena deepens the comprehension of Europa's environment and its capacity to sustain life. Our ground-based telescopes play a crucial role in uncovering the secrets of Europa, positioned on Earth. These instruments provide a vantage point to observe the icy moon and its surroundings. Through advanced imaging techniques, researchers can monitor variations in the surface composition, revealing vital clues about the subsurface ocean beneath the thick ice crust. Our spectroscopy, a method employed by these telescopes, allows scientists to analyze the light reflected off Europa's surface. This analysis indicates the presence of water ice and potential organic compounds, which are fundamental building blocks for life. Observations have shown that the surface exhibits a variety of colors and features, suggesting geological activity that may be linked to the ocean below. The observations from ground-based telescopes are complemented by data from spacecraft missions, creating a more comprehensive understanding of Europa's environment. By studying the interactions between the icy surface and the ocean beneath, researchers can hypothesize about the chemical exchanges that occur, potentially supporting microbial life. In this region of the solar system, where the conditions are harsh, the insights gained from Earth-based observations contribute significantly to the search for extraterrestrial life. The ongoing efforts to explore Europa continue to redefine our understanding of habitability beyond our planet, emphasizing the importance of these telescopic observations in our quest for knowledge. Surface features reveal a complex landscape shaped by a dynamic interplay of geophysical processes. This icy shell, thought to be several kilometers thick, exhibits intricate patterns reminiscent of cracks and ridges. These formations indicate a history of tectonic activity, suggesting that the underlying ocean may influence the frozen exterior. Distinct regions, such as the chaotic terrain, show signs of significant disruption. Blocks of ice appear jumbled, hinting at the possibility of material exchange between the surface and the ocean below. This phenomenon increases the likelihood of chemical interactions that could support life. The presence of surface darkening, possibly due to salts or organics, further bolsters these hypotheses, painting a portrait of potential nutrient availability. Ridges and grooves, often extending for hundreds of kilometers, hint at the movement of ice plates. Such features might provide insights into the ocean's circulation patterns, which are critical for understanding heat distribution and chemical mixing. The varying albedo of these surfaces reflects differences in composition, offering clues about the ocean's interactions with the ice above. Interactions with the ice above. Subsurface plumes detected by past missions suggest that material from the ocean may be venting into space. These ejections provide a unique opportunity to analyze the ocean's composition directly, further informing the search for life in this intriguing and distant environment. The potential for ocean worlds to harbor life expands the horizons of astrobiology research. This region of the solar system is marked by icy moons and distant planets, each with the possibility of subsurface oceans shielded beneath thick layers of ice. The study of these environments could reveal insights into the fundamental requirements for life. This interest has prompted missions designed to explore these ocean worlds in greater detail. Advanced space probes are being developed, equipped with instruments capable of penetrating ice and analyzing the underlying ocean chemistry. These endeavors aim to uncover the chemical signatures indicative of biological processes, providing vital clues about the existence of life beyond Earth. The icy crusts of moons like Europa and Enceladus serve as a protective barrier, preserving the unique chemistry of their oceans from harsh cosmic radiation. This preservation opens a window into potential biospheres that remain untouched. The dynamics of these oceans, including their temperature gradients and hydrothermal activity, are crucial to understanding the environments in which life might thrive. As research progresses, the integration of robotic exploration with sample return missions could further enhance our comprehension. The search for life in these ocean worlds represents a pivotal chapter in astrobiology, illuminating the possibilities of life in environments previously deemed inhospitable. Each discovery adds depth to humanity's quest to understand its place in the cosmos. The allure of Europa extends beyond scientific inquiry, infiltrating the realms of popular culture and reshaping public perception. This celestial body has inspired numerous works of science fiction, where its icy surface conceals the potential for life, sparking imagination and intrigue. In literature and film, Europa often serves as a canvas upon which humanity's hopes and fears regarding extraterrestrial existence are painted. These narratives often portray it as a world of both wonder and danger, reflecting the duality of aspiration and caution that accompanies the search for life beyond Earth. Iconic films and novels evoke visions of explorers venturing into its frigid depths, seeking answers to fundamental questions about existence. This fascination has fostered a collective curiosity, prompting discussions that transcend scientific circles and permeate everyday life. The portrayal of Europa has also influenced public perception, rendering it a symbol of the unknown and a beacon for the ongoing quest for knowledge. It challenges societal norms regarding life, compelling individuals to reconsider what constitutes a habitable environment. The icy moon has become a representation of hope, driving interest in astrobiology and planetary exploration. These cultural reflections may underscore the profound implications of exploring extraterrestrial environments. The challenges of technological development for Europa missions present a unique set of obstacles. The icy crust enveloping this moon conceals a vast ocean beneath, raising questions about how to penetrate this barrier effectively. Engineers and scientists must design spacecraft capable of withstanding extreme cold and high radiation levels, which are prevalent in this region of the Jovian system. But the selection of instruments is crucial, as they must remain operational under harsh conditions while providing the necessary data to assess the ocean's chemistry and potential habitability. Robotic explorers might rely on advanced drilling mechanisms capable of penetrating several kilometers of ice. The reliability of these systems is paramount, as any failure could jeopardize years of planning and investment. Communication poses another significant challenge. The distance from Earth complicates the transmission of data and control signals, necessitating the development of autonomous systems that can make real-time decisions. Power generation also requires innovative solutions, as solar energy diminishes significantly beyond the orbit of Mars. And the pursuit of understanding life in these hidden oceans. Teams of researchers continuously refine their methodologies, driven by the promise of discovery residing beneath the unforgiving ice. Each technological advancement brings humanity closer to unveiling the secrets that lie beneath Europa's enigmatic surface. Emerging data indicate that the icy crust of Europa conceals a vast ocean, possibly harboring conditions conducive to life. Recent missions, such as those conducted by the Galileo spacecraft, revealed a complex interplay of surface features, suggesting tectonic activity. This phenomenon hints at the dynamic nature of the moon's ice shell, where fractures and ridges imply the presence of liquid water beneath. Advanced models simulate the subsurface ocean's salinity and temperature, demonstrating the potential for hydrothermal vents that could serve as a nurturing environment for microbial life. Spectroscopic analysis conducted from a distance has identified intriguing chemical signatures on the surface, including the presence of salts and organic molecules, adding credence to the hypothesis of a chemically rich habitat beneath the ice. Future exploratory missions aim to delve deeper into these findings. Europa Clipper, slated for launch in the coming years, will employ an array of scientific instruments to conduct detailed reconnaissance of the Moon's ice shell and subsurface ocean. Investigations will focus on assessing the Moon's habitability, exploring its surface composition, and determining the ocean's depths and dynamics. These developments usher in a new era of exploration, enhancing our understanding of not only Europa, but also the broader implications for life elsewhere in the solar system. The quest for knowledge continues to illuminate the unknown corners of our celestial neighborhood. The discovery of a hidden ocean beneath Europa's icy crust yields significant implications for life beyond our solar system. The presence of liquid water, essential for life as understood by current scientific standards, opens avenues for exploring similar environments on exoplanets. This region, with its unique blend of energy sources, hints at the potential for biological processes in extreme conditions, suggesting that life may not be limited to Earth-like planets. These findings encourage a re-evaluation of habitability criteria, expanding the focus beyond traditional zones where liquid water exists. A variety of celestial bodies, including moons orbiting gas giants, may harbor subsurface oceans rich in chemical diversity. Such environments could replicate the conditions necessary for life to flourish, even in the absence of sunlight. Forteinse the search for biosignatures. As investigations broaden to include these unconventional habitats, instruments designed to detect organic compounds and metabolic byproducts may be deployed on missions targeting ice-covered worlds. The notion that life could arise in these hidden realms challenges existing paradigms and inspires innovative approaches within the scientific community. In essence, Europa serves as a reminder of the vast possibilities that lie beyond the familiar, urging researchers to expand their perspectives and search for signs of life in the most unexpected places. Planetary science offers essential insights into the conditions that might support life, whether on distant worlds or within our own solar system. Through rigorous analysis of celestial bodies, scientists examine geology, atmospheric composition, and thermal dynamics to assess potential habitability. This discipline employs sophisticated models and simulations to recreate environments, revealing parameters that contribute to sustaining life forms. In particular, the assessment of icy moons like Europa hinges on an understanding of subsurface oceans, which may harbor the necessary ingredients for life. The interaction between a moon's ocean and its rocky mantle can lead to chemical reactions that produce energy, potentially supporting microbial ecosystems. This interplay between geology and potential biology illustrates the significance of planetary science in identifying viable habitats. Observations from spacecraft provide critical data. Instruments designed to analyze surface composition detect chemical signatures that may indicate the presence of water or organic compounds. These findings guide future exploration missions aimed at probing beneath icy crusts. The development of landers and probes is informed by these scientific principles, making it possible to investigate the hidden oceans of celestial bodies. Continued advancements in planetary science are crucial for deciphering the complex factors that contribute to habitability, expanding our understanding of life's potential beyond Earth. Each discovery reinforces the notion that life may exist in forms and environments previously unconsidered. Europa's surface is a captivating mosaic of ice, punctuated by a network of linear ridges and dark streaks. This shell of ice, believed to be several kilometers thick, conceals what is thought to be a vast ocean beneath. The interaction between the ocean and the rocky mantle beneath is crucial, as it may create the necessary chemical reactions for life to thrive. The unique features of this moon include its relatively smooth, young surface, suggesting geological activity, pockmarked with a few impact craters. It exhibits signs of recent resurfacing, indicating a dynamic environment. These ice features, as ionosphere, resembling cracks or fractures, imply the movement of the subsurface ocean, which may be influenced by tidal forces generated by its gravitational interactions with Jupiter. The presence of water in liquid form is a distinguishing characteristic among celestial bodies. This moon is also thought to harbor a salty ocean, which could provide essential nutrients for potential microbial life. In addition, the thin atmosphere, composed mainly of oxygen, hints at complex processes occurring on the surface. Radiation from Jupiter bombards Europa, continuously altering its surface chemistry. These conditions create an environment unlike any other moon in the solar system, fostering the possibility of life in unexpected forms. The complexity of Europa's environment necessitates a multidisciplinary approach, integrating fields such as geology, astrobiology, and oceanography. This collaboration enables a comprehensive understanding of the moon's icy surface and the hidden ocean beneath. Geologists analyze surface features, interpreting the patterns of ridges and cracks that suggest geological activity. These formations provide insights into the processes that govern the moon's icy crust and the dynamics of the subsurface ocean. Astrobiologists contribute by examining the potential for life, drawing on terrestrial analogues where extremophils thrive in harsh conditions. This understanding informs hypotheses about what forms life might take in Europa's dark, nutrient-rich waters. Oceanographers apply principles of fluid dynamics to model the movement of water beneath the ice, predicting how heat from tidal forces may influence the ocean's chemistry and stability. The integration of these disciplines culminates in mission design for exploration. Instruments are crafted to penetrate the ice and analyze subsurface conditions, while advanced imaging techniques seek to map the geology. Each layer of knowledge builds upon the last, creating a cohesive picture of a world that remains largely hidden. Such collaborative efforts pave the way for deeper exploration, highlighting the importance of shared expertise in unraveling the mysteries of this enigmatic moon and its potential to harbor life. Future technologies designed for exploring icy worlds aim to enhance our understanding of subsurface environments. Advanced robotics are at the forefront, equipped with instruments capable of penetrating thick ice layers. These machines will navigate through challenging terrains, providing crucial data about hidden oceans and the chemical compositions that may support life. Innovations in remote sensing technologies will allow scientists to identify potential hotspots beneath the icy crust. These sensors can detect variations in temperature, salinity, and other geophysical indicators, revealing vital clues about the subsurface ocean's characteristics. Such methods are invaluable for selecting optimal drilling sites, minimizing risks associated with ice penetration. In addition to robotics, autonomous underwater vehicles will play a significant role in exploring the depths of these hidden oceans. With the ability to operate independently, they can gather samples and analyze the environment in real time, offering insights into potential biological activity. These vehicles are designed to withstand extreme pressures and low temperatures, ensuring they can function in the harshest conditions. Collaboration with artificial intelligence will enhance data analysis, allowing for the identification of patterns and anomalies that may indicate the presence of life. This integration of technology and expertise fosters a comprehensive approach to exploring Europa and similar icy worlds, driving humanity's quest to understand the possibilities of life beyond Earth. The timeline for future missions to Europa outlines a series of carefully planned steps aimed at unraveling its mysteries. The upcoming Europa Clipper mission, scheduled for launch in the early 2020s, represents a significant milestone in this endeavor. Designed to orbit Jupiter, it will perform detailed reconnaissance of the moon's ice shell and subsurface ocean, utilizing a suite of scientific instruments to analyze the surface composition and search for potential signs of habitability. Following this mission, various proposals for landers and even potential sample return missions have emerged. These endeavors aim to physically explore Europa's surface and collect material for analysis on Earth, potentially revealing the chemical signatures of life. The timeline suggests that these lander missions could commence in the late 2030s, contingent upon the success of preliminary spacecraft. Simultaneously, advancements in robotic technology will enhance our capability to investigate the extreme conditions present in Europa's environment. Innovations in autonomous systems and drilling techniques may play a crucial role in accessing the ocean beneath the thick ice crust, presenting new opportunities for discovery. Funding and international collaboration will influence the trajectory of these missions as the scientific community continues to align their visions. Each step forward builds upon the knowledge acquired from previous explorations, gradually unveiling the complexities of this icy world and its potential to harbor life. The legacy of exploration in this region extends far beyond mere curiosity. It encompasses a profound quest to comprehend the origins of life and its potential manifestations in environments starkly different from Earth. Scientific missions are designed to penetrate the thick ice crust, employing advanced technologies that can analyze subsurface conditions and chemical compositions. Understanding the ocean beneath this frozen exterior may illuminate the fundamental processes that could support life. Insights derived from the analysis of water samples, ice composition, and geological formations will contribute significantly to astrobiology. This endeavor seeks to address essential questions about the evolution of life in extreme environments. The trajectory of exploration highlights the collaboration between various scientific disciplines, uniting planetary scientists, astrobiologists, and oceanographers. Each new mission aims to refine hypotheses surrounding habitability, assessing not only the presence of water but also the necessary ingredients for life, such as essential chemicals and energy sources. Such investigations are poised to redefine our understanding of life's resilience and adaptability. As results emerge, they may reveal the interconnectedness of planetary processes, shedding light on how worlds like Europa resemble and differ from Earth. The collective findings will continue to fuel intrigue regarding this moon's potential for harboring life. Beneath the thick, icy crust, evidence suggests a vast ocean exists, kept warm by the gravitational interactions with Jupiter. This ocean could contain the essential elements for life, offering a tantalizing glimpse into the possibilities of extraterrestrial existence. The surface of Europa, characterized by its intricate patterns of ridges and cracks, hints at dynamic processes beneath. These features indicate tidal forces that could stir the ocean, creating a nutrient-rich environment. Such conditions not only sustain microbial life, but could also nurture more complex organisms if they exist. Scientists remain captivated by the prospect of exploring these depths. Future missions aim to penetrate the icy facade, deploying instruments capable of analyzing the ocean's chemistry and searching for organic compounds. The potential discovery of life, even in microbial form, would revolutionize our understanding of life's prevalence in the universe. The significance of Europa extends beyond its ocean. It serves as a benchmark for astrobiological research, challenging our concepts of habitability. The pursuit of knowledge regarding this moon reflects humanity's innate curiosity, driving exploration across the solar system. Each advancement brings us closer to answering profound questions about our place in the cosmos. Analysis of Europa's icy crust reveals a complex interplay of geological and potentially biological processes. The surface, marked by ridges and cracks, hints at the dynamic activity beneath. These features suggest that the ocean, lying beneath the thick layer of ice, might be in constant communication with the surface, potentially cycling nutrients essential for life. Recent missions have gathered data indicating the presence of a salty ocean beneath the ice, with estimates suggesting a depth of at least 100 kilometers. This environment could harbor the conditions necessary for life, including liquid water, chemical compounds, and energy sources. Theories propose that hydrothermal vents on the ocean floor may provide the necessary energy, similar to those found on Earth. Chemical analysis of the surface has detected compounds such as magnesium sulfate, which could indicate a rich chemistry capable of supporting microbial life. The potential for organic molecules raises intriguing possibilities about the origin of life in such extreme conditions. Research continues into the possibility of plumes ejecting water vapor from the subsurface ocean into space, presenting an opportunity to analyze the ocean's composition without direct exploration. These findings lay the groundwork for future missions, aiming to further unravel the mysteries of this distant moon and its hidden depths. The ongoing quest for life beyond Earth is characterized by a profound curiosity that transcends our planetary boundaries. This pursuit does not merely focus on the potential existence of microbial organisms. It encompasses the very essence of understanding life's resilience against the harshest environments. Europa, with its icy crust and subsurface ocean, serves as a prime candidate for this exploration. The potential for hydrothermal vents on the ocean floor raises intriguing possibilities for the emergence of life, as similar conditions on Earth have led to the development of diverse ecosystems. Rovers and landers, designed to penetrate the thick ice and sample the ocean's composition, are being conceptualized and engineered. These missions will rely on advanced technologies, such as ice-penetrating radar and autonomous underwater vehicles, to explore the depths beneath the frozen surface. Scientists are meticulously analyzing data gathered from previous missions, crafting models that predict the chemical interactions likely to occur in these isolated environments. The implications of discovering life beyond Earth extend beyond mere curiosity. They challenge our understanding of biology and evolution. Every effort made in this pursuit not only enhances our knowledge of the solar system, but also reflects a deeper philosophical quest to comprehend our place in the universe. This search is both a scientific endeavor and an exploration of what it means to be alive amidst the vastness of space.